Go live, guys.
On FB, we're live.
Okay, hello and welcome. Happy New Year from the Prithvi Theatre. Finally, after many months, we are back with Chai and Y at Prithvi Theatre. Today is actually a great day to start, January 3rd. It's the birthday of Savitribai Phule, a pioneer in education, a pioneer in looking at diversity, in looking at many issues which unfortunately still plague the world. Hopefully, we'll make progress towards it. And curiously, coincidentally for the talk today, it's also the birthday of Gordon Moore from Intel. And there's going to be a lot of electronics in today's session. Today, you can't measure anything without relying on some electronics. So, two really pioneers of the field, birthday today. It's a great day to start Chai and Y. I must apologize for this little delay we've had. This is the first time we are doing a post-COVID Chai and Y. I was not aware of the regulations that required the theater to be disinfected for some time after we have completed our setup. So it required some time. And also, I must commend Prithvi Theatre. It's been a fantastic way they have actually set up the screening procedure at the entrance. And also, let me show you. Let me just turn this and show you. Here you see this audience member holding something which looks like a dumbbell. Well, it's not a dumbbell. Actually, it's a very nice distance separator on both sides, so that you come to the theater, you sit on this, and the next person sits only at a safe distance away from you. So thank you all who have braved the times and have decided to join us physically over here. I assure you it's going to be a fun time. For those who haven't, next time, please do consider, if you're in Mumbai and want to come, it's perfectly safe. It's nice over here. We also today actually have a lot of things which we will show you later. Satya has brought a lot of cool looking gizmos and gadgets, which I don't know. They look very interesting. I don't know what they are. Anyway, those I guess will come at some point. But till then, let us try this. We are trying something which I must also thank our team in TIFR. Some people actually chose to stay back there to help us live stream from TIFR, where we know the bandwidth is good. So we are actually on a Zoom call with a group at TIFR who are transmitting this talk to Facebook and YouTube. Now, for those of you who are watching us online, remember that the only way we know what you're telling us is via your comments. So please enter your comments in the chat box or the comment section of YouTube and Facebook, and the TIFR team will relay it to me over WhatsApp, and then we can ask the speaker. It's a little complex, but let's use technology when we can. The audience here, of course, raise your hand, shout, interrupt us. We are here for you. Okay, so with that, it's a pleasure to introduce Satya. Satya, you can come. We can maintain safe distance. I think I'm still sort of visible at the corner of here. So Satya is sort of the man, who most associated with the India-based Neutrino Observatory. But if you want to observe neutrinos, you need to measure things, and he's going to tell us about measurement, which is at the heart of science. And Satya is I think he'll introduce himself. I don't know whether you're an electronics engineer or a physicist or both or everything. But what I will do is, to make life easier, I will hand over the microphone to Satya so he can move around. I will hide with my mask back on and be in the audience and monitor questions.
Hello, can you hear me?
So remember, the mic is only for the online.
Yeah, but
here you talk loudly so everybody can.
Yeah, but I.
Yeah, so we can hear you clearly.
Wonderful, wonderful. Okay, great. Excellent. Good morning, everyone. Those of you who are here, I think it's very inspiring for us to speak to live audience. I think I have been doing this probably after 7 or 8 months. I normally used to do every week on either Saturday or Sunday in one of the colleges in India. But of course, we just got glued to TV, computer screens all along. And it's really great to kind of see some of you here. And I think it will be great to kind of get connected to. But at the same time, the technology has now come so nice so far. I think necessity is mother of invention. That is what we say. But I actually, during COVID, I modified it slightly. And I said necessity and frustrations are parents of invention. So I think there was a necessity, but we were also frustrated. So I think that is what brought us a lot of new technologies. So with all that, thanks everyone. And thanks particularly to the Child team. Obviously, without Suren and Arnab, there is no Child. And it's a great platform that is given. And the platform here in Prithvi adds fantastic privilege to, I came here, of course, first time. I think it's great talking to you on this excellent platform. Right. Arnab left to me to introduce myself. I think there are a few words that are already here. As he rightly said, that I've been doing more than half of my career, roughly about 20 years now, working on this particular project, which is called India-based Neutrino Observatory. But before that, I also worked on many other experiments, the first being a series of Kolar goldfields experiments way back in 1980, and then D0 and CMS experiments at Fermilab and CERN. So about CERN, you'll see a few slides just to make the contact right. And then, of course, now I'm working on INO. Yeah, I did my engineering. That is my first degree. But then I did PhD in physics from IIT Bombay. So I don't quite know whether I am an engineer or physicist, but that doesn't matter. The very first slide that I'm going to show will try to kind of erase this particular vertical wall between these two. So I think it's a long introduction. Let me get to. And as Arnab mentioned, today, for a change, it will be more on soiling your hands and making measurements rather than talking on science, mathematics, biology, computer science, and so on and so forth. So I have spent all of my life in measuring rather than theoretizing certain things. I hope I'll be able to kind of show my excitement in some way, share my excitement in some way on what is the fun and joy of actually measuring things and building things with your hand. Some of them are here. And so that is, so it's little less on science and everything else is kind of measurement. And I kind of made a few disclaimers here, or maybe that's what is 45 thing. Physics essentially is an experimental science. You will also see this word, why I said this, maybe a few slides down the lane. And I also made another statement here, which also will be clear in the next statement, next slide, which is actually mostly spoken. When you say spoken, you speak in language, right? So like mathematics is spoken in physics, physics is spoken in mathematics, but done using always instrumentation. Instrumentation could be detectors, could be electronics, could be something else. And that's what actually brings signals and data into your computer to analyze, right? Okay, so this is my usual first slide. So I kind of try to kind of say a few things about what this STEM is about. Science, normally when we say we want to kind of do something to investigate, but we don't investigate randomly. We kind of do a very kind of, reasoned investigation, systematic investigation. And most of the time we would like to kind of do, yeah, okay. So it's like more like, looking at a systematic way to ensure that what you want to find something from natural phenomena, you want to, at the end, of course, want to understand something new, something discovered, which you didn't know about some of the principles of what the nature is made of or whatever. Now, this is what I said. Many times it's a lot easier to kind of write down the science that you want to do by a nice equation. I don't have to say there are many famous equations which are coming to your head when I said this. And so often one say that maths is a kind of mother tongue of science. So you actually speak physics in terms of maths. Now, very often, again, I don't have to say examples. You can say your own. You can bring your own examples. It could be GPS. It could be cell phone. It could be any other things. Once you have science, when somebody Maxwell tells you something, once Einstein tells you something, you actually get down to kind of mitigate or manipulate the science that you learned into trying to do something which is probably useful for humankind. Okay, so Maxwell told, let us say electromagnetism, Maxwell's equations brings you something like cell phone or many other devices. Maybe law of general theory of relativity will bring probably to GPS. We can't work without those principles. But that's how these technologies try to make a connect between these two. Then you might say that where does engineer comes in the picture? Because obviously, if I make a cell phone which costs $200,000, or if it weighs 200 kgs, or consumes 1 kilowatt power, etc., nobody is going to use cell phone, right? I want to have little phone in my pocket, it, which can also kind of don't make a deep hole in my pocket, maybe cost 300 rupees, maybe charge once per day, and it should be able to kind of work, etc. So optimization of resources becomes very important, whether it is size, weight, cost, power, whatever it is. The engineer really works on trying to bring this device to affordable level in all senses, right? So that's where kind of engineer comes in. So I again try to make a small change in what is most commonly known, so-called two sides of the same coin, but I actually introduce the third surface that actually connects the two sides and say, scientists, engineers, and technologies are, I don't say sides, but three surfaces of the same coin. So please remember the annular surface that you have. So quite often, we, as I don't know how many of you are either studied engineering or well into that. So we often say branches of engineering. We actually say electronics, civil, mechanical, and so on and so forth. And here I say all these branches of engineering are actually in some way goes back to, always traced back to the roots of science. Okay, so it's the science that's the root of this tree, probably whose branches could be like this. So if you are an electronics electrical person, probably, and you can actually see at the roots, there are names of these people whom we learned in the school and college, and you know very well, many of them are actually well-known scientists. They really tell you the foundations of this tree, the roots of this tree is actually done by these guys. And when the tree grows up, there is one branch which is actually called today as an electrical engineering. And similarly, it is called electronics engineering. Again, I'm not going to read all the names that you have. And you can even go to mechanical engineering, right? You can see the scientists who laid foundation for this branch. At this moment, I also want to tell you that every time there is a new branch of engineering, some of us oldies, when we studied engineering, there are only 3 or 4 engineering branches, but there are many more now. Every time a new branch literally comes off the tree, actually there is a foundational work that was done in the branch of science, right? Even things like civil engineering, right, has similar kind of roots. Some of us belong to this particular branch of the tree, which we work on nuclear engineering or high energy physics and so on and so forth. Again, we have our own deities in some sense. We have our own pioneers and foundation scientists on this. Okay.
So hopefully in the next 20 years, we'll see more Indian names in these.
That's right. Well. So this is important. For example,
all of them, most of them, minus 1 or 2 were white males. Hopefully we also see diversity.
More of, yes, that's right. I mean, good enough to bring this. For example, optics, right, become a big engineering subject right now, right? Many of the colleges started having subjects which are no more core. There are undergraduate courses coming up in AI and machine learning, etc., which are used to be very specialized. So there are people in the Indian context, guys working on it. I'm sure one day we'll see more of those names. And also, as you rightly put in, lots of now. If I can say, women scientists are becoming increasingly popular at the workplace. So thanks, Anna, for bringing this house. So when you say there is a big space, and then where do all of us stand, right? Maybe in this space, all of us stand in these vertical 3 columns. Now, if you are a guy who is so-called original thinking, belongs to that, then probably science is something comes closer to you. Probably you'll end up doing research. And if you're a person who is very innovative on your thinking, right, and you are kind of person who always works on technologies, maybe you'll become somebody who will develop techniques based on the scientific principles. And you are a real practical, people say he's a very practically minded person, and then you look at engineering as your core, and then maybe you will probably start designing lots of stuff and then sell them. Okay, now when we talk for the rest of the portion today, probably we'll keep using words like high energy physics. We use words like particle physics and so on and so forth. For those of you who kind of a little unfamiliar with this, that's what is kind of given here. You can really start with any solid, any object, anything matter that you see around, including this pointer, including myself. We are all, of course, made of matter. And then you can get down to molecules, atoms and nucleus, etc. We all study this in school. And now inside, of course, if you go into nucleus, you have nucleons. Nucleons are nucleus. Atom has basically electrons and nucleus. and nucleus made of protons and neutrons. And then protons and neutrons. In fact, when I joined TIFR, that's all we knew, right? Sometime back. But then now we know that protons and neutrons do have structure inside, and now we know they're called quarks. And we also know most of all these particles have been kind of discovered already by laboratories. Okay, so this is the kind of roughly the kind of field that we have today. Now, particle physics, in some sense, is this kind of modern version, or maybe an effort that we all know about to understand the laws of nature, which I mentioned about in the definition of science. And most of the time, it tries to kind of answer the following two questions. What are the basic constituents? Where all we can go? We can't go beyond at the moment. Let us say quark. And then more important and more interesting that is that what are the kind of forces that govern all these particles, that we kind of have that can predict or control the behavior of this kind of particles. So the game is to actually make particles interact and study how they behave, and then try to understand their features and so on. So the last line.
Use this point.
Okay.
Use this.
Yeah.
Then I think both people, they'll see the pointer on the screen, I hope.
Yeah, they can see. Yeah, but then I'll be stuck here.
Yeah, but at least both
Okay.
that audience and this audience will probably get something, because otherwise
Okay.
that audience sees the back of your head.
Okay, fine. So now I'm really coming to the bottom line. The bottom line really says that, what is the kind of thing to aim is to measure various parameters that are governing it. Sometimes could be energy, sometimes could be direction of this particle flux, and sometimes you have to really identify what happened and who is, identity of this particular particle that we have precisely as possible. So the rest of the talk is actually mostly aimed at this particular line, which says only when I can accurately measure things, only when I can accurately identify the guys that are produced in this reaction, only when I can find out from which direction it is coming, right? Each one of them has a profound connotations, because, for example, for astronomy, I mean, even if I have everything else very nicely done, but I don't know from which direction it is coming, then I cannot do astronomy, because astronomy really works on that aspect. And similarly, if I'm doing high energy physics, I need to measure the energy of these particles very, very accurately, because I would like to know whether this has come from this particle or this particle or this particle. The only way, I mean, one of the most common ways is actually sum up the energy and look at. And if I don't identify, if I don't know what particle it is, it's like a black magic. So therefore, the measurement plays a big role in this thing. So before I dive down into actual some of the slides, I know many of you probably are aware of, but it's good to kind of know the scale of these kind of things in the powers of 10, right? Many of us use, thanks to nano cars, so we know 10 power minus 9 is nano, but I mean, there are also numbers which are as small as pico, which is 10 power minus 12, and also of course femto, which is 10 power minus 15. On the other side too, you have many of us, of course, know, we also know mega, but then there is giga, which is 10 power 9, and there is tera, 10 power 12, and peta, which is 10 power 50. It's important because we keep using these words very often, and we need to kind of get the dimensions, both on the very small size and very, very big size, okay? And also, I want to give one slide on this magic of how guys like what is actually written here, either Einstein or Boltzmann or Planck, they kind of did a fantastic job of making an interconnection between mass, the energy, distance, temperature, and time. I can actually talk about in any of these units, which looks very strange in the beginning, somebody talking about mass of the particle and try to give in electron volts and so on and so forth. But the electron volt, as you know, it's an electron volt is basically what is the energy? That is very tiny energy gained by an electron when I actually pass through in some field, right? Which is produced by 1 volt. So I take 2 plates, connect 1 volt, I pass an electron to move, and the energy that guy gains the passing is something electron volts. Of course, as you can imagine, it's very, very tiny. But here you can really see energy is connected to mass and the speed of light. It is connected to Boltzmann constant and the temperature, and it's here Planck's constant, the speed of light and wavelength and so on. All these allows us to kind of speak at the quantities very interchangeably. So for example, sometimes it's a mass of electron, but actually I give an electron volt half an MeV, and it's a mass of a proton, which is roughly about 200 times. Sorry, not 200 times, it's 1 giga. And electron volt, I can also kind of express in temperature. I can also express 1 GeV in terms of, let us say, femtometer, which I already told you it's something like minus 10 power minus 15. So this is great because when you actually do measurement, quite often this conversion becomes very, very important and useful. You will see them later. Another thing I'm going to kind of little bit load you very early in the slide is to give this kind of a periodic table of particle physics, something similar to what you see in chemistry. Periodic table is, of course, quite big. I think has hundreds of elements, but luckily here there are only a handful of them, right? But don't worry too much at this moment if things are not kind of gone, comprehensible at some stage. It's not important. I want to introduce this like a play, and these are the actors in the play. We kind of roughly should know who the actors are, right? Normally in the play you have the titles scrolling up at the end, but here the titles are in the beginning. But even if you don't know the names of them, because they will be acting, you will actually know, that guy fat guy and this fellow fair lady or whatever. So you will actually, you don't have to really know the names and those characteristics very well. But just look at this. So you can actually see there are color codes. So these pink ones here are called quarks. By the way, the entire thing here is called fermions, right? So there are 6 quarks. I already introduced to you earlier 2 quarks at least, and I said up and down quark, which made protons and neutrons, which are called nucleons. By the way, this entire column is called generation 1. There is generation 2. There is generation 3. There are 3 generations of them. And there are also, at least one of them is very familiar to us. There is also a heavier cousin, which probably about 200 times heavier cousin. This is muon. And even more heavier one is called tau. And similarly, these are the heroes for the rest of the play after after kind of first half. These are called neutrinos, very, very tiny, very, very tiny particles. But you should also see there is one corresponds to each of these leptons here. So there is a electron neutrino, muon neutrino, and tau neutrino, and so on and so forth. So these are leptons, and these are quarks, and so on and so forth. And most of these were discovered. I mean, everything is discovered in that sense. What you see here on the table, and in fact, I feel kind of very lucky to kind of know myself that okay, I was part of this experiment which discovered top quark in mid 90s. And then if you come to the so-called force carriers, you have of course gluon, which makes the entire nucleus to bind together in a way protons and neutrons together. Strong force we call. Photon, of course, is the omnipresent electromagnetic carrier. And then Z and W are the ones which actually most of the interactions that takes place in the leptons are taken care by the so-called weak interaction. This was discovered much, much later, only recently, 2012. Okay, and of course, he was given Nobel Prize in 2013. The only reason that it was discovered almost 60 years after it was kind of strongly enunciated is the technology. So when you have technology that is ready and available for doing research, and that is the only one that blocks from discoveries. So you will actually find quite often in the talk that quite often it is the technology that is available which will make or break for what can be done in science. And the accelerator technology, the detector technology, computer technology, etc., were required to kind of go ahead and discover this kind of heavy particle. It takes a big accelerator and so on and so forth. So this is what we know today, which actually manifests mass to all these particles in the table. And that was also discovered. So I was also happy that I was also part of the team. And in fact, the co-author of this paper, which went ahead and gave Nobel Prize to Higgs and Peter Higgs and other people. So this is the kind of picture that you can imagine. And when we kind of talk now more and more of these kind of yeah, okay. I think that's what is going to kind of keep coming again and again, right? So let us look at what is in store, right? Now, when you say that you have, let us say, measurement or certain probing, right? Now you can see on the left that you have something like a screen at the middle, right? Can you see the screen, the kind of a scale at the middle of this figure, which starts from all the way from something like 10 power 26 meters all the way up to 10 power minus 34 meters. Now, if you call this as a Big Bang, this is the kind of scale of objects that you want to measure. And obviously, when you have nebulas, when you have Milky Ways, when you have the entire universe, the sizes are much bigger. And you use, of course, telescopes, which are on the left, the instruments that you use, like Hubble telescope, for example, one of them. Now, if you get down to kind of looking at scales which are something like diameter, radius of Earth, diameter is of the order of about 12,000 kilometers. So you kind of use, let us say, dish antennas or equipment, something which to kind of monitor a measure. If you want to take a picture of a person running around, use, of course, camera. If you want to go down to look at, let us say, the DNA, the virus, etc., use, you know, microscopes. But if you want to go anything below, if you want to start studying atom, what happens, nucleus, if what happens, the, as I said, protons, neutrons, and quarks, and so on and so forth, you start building these little accelerators, which are typically circular objects into which you kind of accelerate certain particles and make them collide. That's why they're also called collider. But with all this, you can see that the limit that we have reached is more of 10 power minus 16 meters. It's still a long way before you can go all the way to what happened at the Big Bang. So in a way, you might say that what we have been seeing is doing physics that happened, let us say, at the time of Big Bang. And how close we can go down, it depends on what are the powerful tools that we have. So we started way back, and then now we reached somewhere like midway between what we are, and then where we are heading to. One basic principle that we should always remember, whenever I want to measure or whenever I want to record certain object, let us say the distance of that or the let us say size of that is some value. And if I want to use it, probe it, using certain radiation, I should ensure that the wavelength of that probe radiation should be always much better than, much smaller than the kind of object that I am looking at. There are some examples you can see. If I want to understand what an atom is, I use X-rays, for example, because atom is 10 power minus 10, and the X-rays are about 10 keV. Similarly, if I want to probe, obviously, nucleus, then I need a higher one. If I want to go down inside and look for example, the nucleons, which are proton and neutron, then I need to go further. And just now, what I told you about LHC and the Higgs boson and that kind of research, and we are going down to tera electron volt. That is what the LHC is made of. Okay. Okay.
So maybe this is important enough that
yeah. Yeah.
That if I want to measure something of some size, I need to
so
if I want to feel a ball, I can't feel it with something which is this big.
That's right.
I need something small.
Smaller. And now you go further and down and say that I have objects which are 10 power minus 10, 10 power minus 12, 10 power minus 15, and so on. I mean, I need to kind of have a probe, whose wavelength should be much smaller. On the other hand, you can convert into energy right away. That's what the thing that I showed you. That means if I want to probe deeper and deeper into matter, I will require accelerators or projectiles or whatever word that appeals to you, much higher and higher energies. So if you can't build a very large accelerator, very large energy accelerator, you will not be able to probe beyond certain things, right? So therefore, it becomes very important as I go deeper and deeper into the structure of the matter, I need to be equipped with this massive accelerators. That is one of the probe. By the way, there is also another school of thought, which is like non-accelerator physics, if you want to call that. Okay, so instead of making man-made accelerators, and you have a limited thing, right? You can't really make a big thing. Now, for example, let's say I'm going to show right now. Maybe I'll keep that word aside, but there are also accelerators in the universe, right? There are also accelerators which accelerate particles coming from beyond our solar system, beyond our galaxy, and the fields that exist in the universe are so heavy. They accelerate these particles. Let me tell you, many orders more than what can be done in man-made. So if I'm looking at on the Earth and sitting there and looking at, I'm actually looking at those particles which are already accelerated by nature. I can also use that physics, which is complement rather beyond accelerator physics. So it's not that everything can be done in accelerators, right? There is lots of physics that can also complement on the non-accelerators. And believe me, so these accelerators are man-made, whereas the accelerators that are existing in the universe are those which are natural, and neutrinos, in fact, are one of them. I'm going to touch upon a little bit on that side. Yeah. So I just want to, again, these are all publicity slides that I make just to kind of elevate myself. Why an instrumentation engineer or a person who does measurements is very important. Here, what I shown is on the top, you can see there are very classical kind of detectors. I am not going into any details as of now, unless you have questions about it. They are sometimes called, there are cloud chambers, there are bubble chambers. These are like photography films. I can actually click a picture and then get a trace of this particle and so on, and I develop the film and I get similar. But there are no electronics involved there, so these can be called as non-accelerated electronics, or the detectors. The one picture below, you can see that there are people standing there, and there's a rectangular object which is actually has wires on X and Y. There is a certain gas that is flowing through, and if I shoot a particle through the perpendicular to the kind of screen, it's going to produce certain signal on X and Y like a crosswire. I'm going to kind of show this. This was actually done. This was actually you can say invented by Chepak, who is this person. And very rarely Nobel Prizes are given for people who invent detectors, and he's one of the earliest one. So he's always like a godly figure for us, because he Nobel Prize coming for a person who designs detector is something very not very common. Okay, so these are so-called electronically read out detectors. Lots of particles which were discovered using this device. That's why he was given Nobel Prize. But these are no less. You can actually see I've written in what are the particles that were, including positron, muon, etc., were actually discovered by these classical detectors. Now I want to show you this particular slide to say here, what are all these that you see here are actually the detectors that were developed by people at different points of time. And some of them probably also won Nobel Prizes. I have written in the orange color. Now there are gaps in between, right, in this slide. Now if I go to the next, you'll actually see in white all the discoveries that were made using these detectors. So this is what I was trying to say, that, I mean, the instrumentation, the detector, the electronics, and data acquisition systems, whatever it is, they play a major role in science development and science discoveries. But that doesn't mean to say that science is only receiving benefit from detector. But a lot of science that is done today goes behind the instrumentation that we develop tomorrow. So obviously, this is a both are beneficiaries as well as catalysts to each other, right? When we talk about measurement, always these are words which keep coming again and again. So I kind of try to give some idea to you. I mean, of course, we all know what kind of dimensions of certain things. We keep talking about, microns and so on. We talk about looks like a big trunk of a tree, but believe me, this is a human hair, which is like 50, 60 microns. Of course, Arnab works in semiconductor devices developments nowadays. The scales of those are going to 5 to 10 nanometer level. He talked about Gordon Moore's birthday today, and of course, he's the guy who actually predicted how the devices scales are going to happen. On the left, you see that how we typically measure things, right? We kind of take a tape, try to kind of see with the pencil, we mark where we are. And please remember, how well we can mark on that particular dot. This is actually, let us say this is the inches, for example, or the centimeter, it doesn't matter. But how well you can mark between these two lines is the maximum, you can say, the resolution that you can get in when you mark by your hand, right? And different people will mark a different way on the same. But sometimes you use some little gadgets which are called vernier calipers and so on. It will improve your measurement, but that's about it, right? Now, when you do a physics experiment, you say that, look, I mean, this is a value that I want to kind of discover, I want to kind of identify. But then the point is that I can never really exactly get the value where theoretically, let us say, proposed. So when I actually measure, it is possible that I get a value which is somewhere sitting here. And now the difference between the value that I want to refer to and also the value that actually I obtained is here. This is vertical line, the central line is what defines as an accuracy. Now, why? It's not just one line, but it's actually like a bell. It's like a distribution. That is because every time you kind of measure, it doesn't mean exactly like that putting a pencil on the dot. So different people for the same value try to put, there will be a next digit, a previous digit, and so on. And if I make thousands and lakhs and millions of samples, it actually follows what we call Gaussian distribution. Now, that is one. So how narrow this is will give me an idea about how precise the measurement is. In fact, if your instrument is absolutely infinitely precise, you will see just one straight line going up. Whereas if your value is absolutely accurate, it will sit right on the reference value. But so this value tells you how accurate it is, and how small or wide this is will tell you what is accurate. That is something like saying what I've given a picture here. You can see that if it is if I start hitting stones on those concentric circles, which is I think dot game, you can actually see that this is very, very accurate because everything is kind of falling pretty well on the same line, but it is a low precision because one dot here, and one dot here. It's not very precise, but it's very accurate. Of course, this is very, very precise, but it's far away from the central value, so it is less accurate, right? So
if you want the gold medal, you have to be both precise and accurate.
exactly. If you want a Nobel Prize, I think it is important that the value that you measure, you remember I showed you Higgs boson, I said 126 GeV, then it is important the error on that are as low as possible, right? And so of course that is it's a big game to play. You will actually see right away how tough it is to kind of reach out to that one golden event. Here I showed a picture which all of you must have seen in some way or the other. This is of course the so-called Big Bang pattern, but what I actually did on this is I juxtaposed all the major science experiments this country is actually involved today. Okay, and you will be surprised. I was surprised when I started making this picture that I mean we are doing rather well in India. If you look at from the all the way to Big Bang, which is of the order of 10 power minus 43 seconds, right? You are sitting right close to that. The physics that is happening is what India-based Neutrino Observatory is doing. That is where I proudly belong to. If you go slightly to the right, you will find something like 10 power minus 32 seconds, and that's exactly what physics that is happening CERN is trying to do. I was happy that I was also part of CERN. Now you can keep moving towards the right. You will actually see something called a flare, which is a couple of minutes after the Big Bang. You can move further, square kilometer array. Suddenly you will find 100 million years and so on and so forth, right? So this is what you call SKA. You can actually see, I hope. And then there is another experiment called 30-meter telescope that is suddenly 500 million years ago, and 1 billion is ITER project, which is also working on fusion of energy. And then there is a LIGO experiment about which you must have heard about. It is few billion years ago. And ultimately, of course, 10 billion is where the solar system is formed. And 14 billion years ago, the Big Bang has happened. And we are actually looking at probing science all the way. And Indians are involved in a big, big way. Some experiments are actually located in the country itself. Some of them we participate going outside because it requires fantastic amount of instrumentation, accelerators, etc. As I told you, it is not enough. It's not possible for one country to kind of do that kind of science.
Sorry, there are two questions on coming in.
Yeah.
Live.
Yeah.
Avina wants to know what is the exact size of an electron.
Okay.
We know it.
Yeah.
And are neutrinos the tiniest known particles? And if there is something like a size for a neutrino?
Yeah. Okay. So this picture should give a feel for it, because I kind of talked about the sizes and here. Okay. Now, so this is electron is 500,000 electron volt, right? So now you need to kind of convert that using one of these equations to get what is, for example, for roughly for 1 GeV. Okay, 1 GeV is 10 power minus 15 meters, right? And so this is 1 million is like 3 times, so 10 power minus 18. So half into 10 power minus 18 is the number that you should look at for. Whereas neutrino is 1,000,000 times smaller than an electron, roughly. So if you want to kind of get a feel for how small a neutrino is, about 1,000,000 times smaller than an electron, and then electron size is what we said, something like 10 power minus 8.
Okay, and since you showed the slide on the family of all the possible periodic table of particles.
Yes.
Raj is asking, how likely are we to determine a new particle, or do we already know that these are the particles?
Okay, so science is again science is again something which only you can do as much as the collective wisdom of the current generation can do, right? For example, Higgs boson. It was predicted way back in 1960s, right? Okay, because when you kind of do certain probing, you do think that we have reached end of top quark. All the 6 quarks are done and identified. But you always look at some things which are as fundamental as, fine, I have so many particles, they have different masses, etc. But who gives mass to all these particles? There is no evidence till that time. So people really started looking at this particular boson, which is not one of those 4 bosons that we already know about, namely gluon and photon and both Z and W. But one is looking for another force carrier, which we call Higgs boson, which actually manifests mass to all these particles. Now, evidences of those things come from collective, results. It's not that somebody wakes up and suddenly finds out, there must be an Higgs boson. There is always evidence coming from various experiments, various results, and then pointing out to something which probably there. So therefore, theoreticians start working on it and kind of say that there may be a field, there may be a particle responsible for this particular force carrier. And now probing that, I mean, firstly, theory has to be matured enough so that it warrants an experiment, and then you put billions of dollars of that, on experiment and try to kind of read that, right? So it is never an end to that, saying that, do we have, I mean, did we discover everything? No, the picture can never really be complete. I was very happy when I was giving talks before 2012. This picture used to look very nice and symmetric. Okay, now you find one guy sitting off center there, right? So, I mean, it really happens like that. It really happens many times. We need to kind of look forward, and there will be always physics which is beyond what we can think. So nobody can say today we discovered everything, all the particles that are required on this, right, on the Earth. Yeah, so I was kind of talking about it. So what I'm going to do is, great. What I'm going to do is, I just take two of these experiments. I wish I could take all of them, but I want to take just the first two. And also it so happened that probably I also worked on both of these experiments. And I'm not going to kind of go so deep into science and say what they are meant for, why they are built, but I want to kind of say, what is this interesting, what is this exciting game of actually building things in order to do the science that these experiments are supposed to do. The first one, of course, I go a little fast because that is an experiment which already many of you probably know. You have kind of understood what it is. So the so-called LHC tunnel, where the two protons are going to they get accelerated on clock and anti-clockwise. This tunnel is about 28 kilometers in circumference, and literally it straddles between two countries. One is here, France and Swiss. And there are precisely at 4 places, there are actually these experiments, very gigantic experiments. They were built there. And of course, I belong to the CMS experiment here, but there are also other major experiments called Atlas, right? You should remember these two names. Now, the protons accelerating at very high energies, which are possible because there are a large number of magnets which are mounted on this ring. They kick the charge particle as they come closer to kind of this particle. To that place, and when they attain certain energy, remember I told you something like TeV energies. Okay, they're made to collide each other head on, something like what is done here. Now this is the close-up picture. You can see that one proton coming from this direction, another proton here, and made exactly colliding each other and producing a splash of these particles, which you can see by these traces of those tracks. And incidentally, I mean, they produce hundreds, thousands of tracks from each of these events. It is a mind-boggling job to be able to connect up these tracks like a dots on a graph sheet. They are all separated only by tens of microns, and it is extremely difficult. Right away, let me tell you that the techniques which are used to kind of do this track fitting, or the techniques today, they are there on all over the industry, as pattern recognition algorithms on machine learning, AI, and etc. These have been kind of identified 25, 30 years ago in the particle physics kind of thing. Look at the data that is produced. Every 25 nanoseconds, you produce megabytes of data. You can imagine how much data you require to store. People talk about their big data analytics, etc. These numbers go above all their kind of heads. Now, when the tracks are formed, when the splash of these particles are produced, you can see they're actually going through something like an onion peels of this various detector, different color, and as they go through, they leave tracks, and that's exactly what is of interest to you, right? So the same picture I kind of make a cut out and kind of trying to show here. So this is where that kind of collision happened, and you can see these particles flying through those peels of onions. And believe me, each of these detectors are, I mean, it's a mind-boggling in terms of the detector construction, their operation characteristics, their capabilities. I mean, you can talk for days together on each of those detectors. But what is important is to know different detectors try to identify, measure these quantities. Remember, I mentioned to you for different particles. For example, you can see there are different colored particles, and as they pass through, various detectors are trying to measure their identity, measure the energy, measure the direction, and so on and so forth. And when you actually put all this data together, is what makes you to kind of to get a bigger picture. And look at this size. It's one side is about 7 meters, so it's about 15 meters end to end. Okay, just to give you a perspective about how big these are, you look at this person who is standing here, and these are the objects of the detectors. Okay, this is just a piece of the detector. This is not the complete one. And there are thousands of scientists work on one experiment like this, and it takes 25-30 years to kind of build such a detector. Now here is, I want to kind of pause a little bit. I want to say, now if you look at on the left, there's a huge list of tables I mentioned for experiments like an LHC. What are the detector technology? What are the technologies that are at work? And many of them we call, I mean, all of these I don't want reading, but you will find that these technologies are not that something developed and people started working on, but many of them required, they're beyond state of the art. Actually, the science experiment kind of you can say probe the technologies to invent new technologies so that they can be utilized. Then you can cryogenics, you can call optics, you can call electronics, you can say computer, data handling, all of these technologies. There are 30-40 of them which are actually become so matured, and now people actually kind of use them. They are actually available for technology transfer and so on. On the right, what is shown is a very, very high density silicon detector. The vertical lines are actually of the order of about few tens of microns. You want to see when the track is coming out of the center, how well you will be able to mark them and connect them. This requires such kind of detectors, right? Okay. Electronics, I mean, those of you who are probably have a flair for electronics, you need 20-30 million detector channels to be instrumented. Each signal is so tiny. If you go to ECG machine, probably you will see about 10 or 12 probes that are stuck on the body. The signals come very slowly, maybe about milliseconds is the speed. Here you have 20-30 million detector channels, and they come at every 25 nanoseconds, right? And each one of them is about a nanosecond wide. So how will you build electronics for it? And you make sure that the total consumption of the power is very less and so on. It's a big, big challenge to build electronics for such devices, right? That is what I said. Thousands and thousands of scientists, engineers work on one experiment. The paper, if you see the Higgs Boson paper that was published by us, it has 3,500 authors in one paper. Okay, the list of authors itself, I think, are 6 or 7 pages, right? And now you have Atlas, another experiment. Again, they have about 3,700, 3,500 authors. There are 7,000 PhD scientists working in one campus to do one single physics, spending billions of dollars. Some of you already must be thinking this is nothing but just madness, right? Yeah, I agree with you. Okay, but this madness, the amount of technologies that it has brought about, and it is every day something new coming up, and it's opening up the entire universe into doing something. There are thousands and lakhs of Indian students go to CERN to do internship. Their life changed forever. They go for doing internship for 1 month, 2 months to CERN. You don't have to look at that boy or girl. They must have really done fantastic work later. So that is the kind of power of the science collaboration that really happens. I call this as a social engineering. It's not just science alone. How do you, I mean, if you have Tata or if you have Reliance or something like that, you have, let us say, 10,000 people, but 10,000 PhDs sitting together in one campus in one roof, literally like this, you can imagine how tough it is. Okay. And these spin-offs, I mean, every day there is a new spin-off. Probably this is the most visible spin-off of LHC, right? We all know this way back 1990. Imagine this person patented or asked for royalty of www, right? You can't imagine. You would have actually been maybe from here to moon. You must have had money stacking up. People go and actually nowadays call farm computing. They call many other grid computing, cloud computing, and these are all required for LHC data to number crunch. Literally, all the computers in the world were combined together, joined together for high-speed network, and they throw data into any of these computers. The data doesn't even know whether it is being crunched in India or South Africa or Korea or Malaysia. You don't know. Okay, and the data comes back to CERN, and it's like a concentric cycle. There is a tier 0 where all the data is produced, tier 1 and tier 2, and so on and so forth. And what kind of computer technology? More important, what kind of communication technology that requires very, very high speed networks to throw data and coming back, right? And these are today nobody knows. I mean, people use it, right? People use it because the technology has come into place, thanks to LHC, thanks to CERN. After all that hard work, billions and billions and billions of events, one was looking for just this one event which is on the screen, right? And it is telling you that precisely when I have Higgs particle going into so-called 2 gammas or 2 jets, and such a clean signal across thousands and thousands of tracks, okay, how do you identify them? It's, people say needle in the stake. I think the needle in the, but that is, I think, a very small kind of comparison I can tell you. When you have billions of such flashes coming out, there is one event that is Nobel Prize work, and the software has to kind of, you cannot do it by yourself. The software has to identify that wins a Nobel Prize, and that is this particular event. It happened, and July, I think 4th, I remember well, July 24th, 2012, we made an announcement that we actually found Higgs boson. And very next year, 2013, these two gentlemen, actually there are 4 of them, they won Nobel Prize. And if you read the citation, it clearly tells that for theoretical discovery of mechanism that contributes to the understanding of origin of subatomic particles. That is what I have written in blue, in yellow. But look at the white part, and which recently was confirmed through discovery of predicted fundamental particle by Atlas and CMS experiment. Actually, we all owe Nobel Prize maybe $1 each, because there are 7,000 people, right? So you have to divide Nobel Prize. But what I want to say more seriously, that is what first line I mentioned, physics is an experimental science. This person, he told during this, in fact, this photograph was taken when we announced the discovery in CERN in the main hall like this. And after that, he said, I'm really happy to be alive to see that this can be discovered in my lifetime, because he waited for 60 years. Okay, that is the power of experimental science. Unless you prove, unless you measure, unless you show, the theory, however powerful it is, it cannot be just taken for granted. Nobel Prize cannot be given. You do 2016 gravitational waves, 2017 you get Nobel Prize. It has to be. If it has to wait for a century, Einstein did it more than 1 century is over after he had predicted gravitational waves. No Nobel Prize. Why? Because they are not discovered. So that is power of doing things by your hand and experiment. Now I want to quickly change. As I said, this is the first part, but the second part is the experiment where I work on. You would have seen in those the table, I kind of try to show those tiny particles, which one of the questions that was asked is like, how small is this particle? Is extremely tiny. If electron itself is a tiny, then it's a billion times smaller than that. And in fact, after the photons that are filling up the whole universe, this is the next, I would say, the most abundant particle, right? If you have like something like 400 photons per cc, maybe you have 300 neutrinos per cc kind of thing. Of course, there are no direct measurement yet, but there are attempts to do it, and they're very tiny. They don't lose energy as they pass through. So you see trillions of them, literally, neutrinos which are produced in sun, produced in supernovae, produced in maybe Big Bang, right? Big Bang 14 billion years ago, the neutrinos which are produced, they're still hovering around because they can't be stopped. They are called relic neutrinos. I'm sure we are all bombarded with all this. And as I'm giving you talk today, you will be surprised to see you have been bombarded with trillions of the neutrinos. Obviously, they do nothing to you because they just pass through. If you really want to stop a neutrino, probably you have to put billions and billions of people in one straight line and shoot a neutrino. Maybe at the end of that, maybe one neutrino might be kind of stopping. It's absolutely harmless. But I want to also say something quite interesting about these neutrinos. There are always fears about, the neutrinos coming from sun or from anywhere, atmosphere or whatever it is, very dangerous and so on and so forth. You will be surprised that we are actually made of certain radioactive chemical in our body. Potassium 40, for example, many of, I think, Arnab and others also work on it. Very tiny portion of this radioactive element. It produces neutrinos. These neutrinos which are produced outside, they can't be stopped. They can only just go into space, eternally. So which means in some way, we are actually producing neutrinos, a large number of, maybe about 300, some number probably there, 340 million neutrinos per day. Okay, we ourselves are a big source of neutrinos, and maybe those neutrinos are specific to you. I think they're representatives of you, they're signatures of you, and they're permanently there in the universe. It's very interesting. I want to sometimes I sometimes give an anecdote, but I'll avoid giving this now. Maybe at the end we can talk about. Okay, so you have signatures of yourself. All of us have our signatures in the universe eternally. You don't have to take ashes after somebody passes away and immerse in Ganges or Godavari to kind of say you have your signatures eternally there in this universe. Okay. By the way, sun produces neutrinos. Without sun producing neutrinos, it cannot actually give light. So-called thermonuclear reaction, right? 4 protons combine and form an helium, and it produces precisely certain energy, 27 MeV energy, and also it produces neutrinos. So without neutrinos, there cannot be thermonuclear reaction happen in the sun. That means there is no light, there is no heat, there is no life on the earth, and you and me won't exist. So interesting kind of insights. I mean, this is just an example, again, more for outreach kind of a thing. You can see that all of us, of course, eat bananas. I don't know if you're a fan. I'm big fan of bananas. Okay, if you take a typical banana of 120 grams, you'll actually find, again, the same potassium here, right? Out of that, probably a small, maybe about 50, 60 microgram of potassium 40 can actually emit something like, maybe 12 or 13 anti-neutrinos every second. Okay, obviously we have been using bananas, eating bananas in generations, and I don't think we had any problem, and so are they're very safe, and the neutrinos are also safe. Okay, going back, a couple of really classical experiments. These guys here, Reines and Cohen, they first discovered the neutrino way back in 1950s. Okay, 53, I think 55. They went to a nuclear reactor which produces neutrinos, and then so when you see an incident neutrino, actually in this case an anti-neutrino, you will actually see that if you use water as a big tank of water, and then you fill it up with a cadmium chloride, that is the material that was used, the neutrinos which are coming in will actually interact with you can see with the protons which are part of the water here, and it inverse beta decay, and then you actually see it produces a neutron, and then also it produces a positron. Now this positron and an electron that is already there, when they annihilate with each other, it produces 2 gammas which go back to back. You can actually see those. Okay, so you have to discover these, and then it will also happen this neutron which is produced goes and interacts with cadmium and produces an unstable cadmium 109. After some time, it also makes a stable transition and produce 1 gamma here, right? So the idea of being able to discover a neutrino, you should look at these 2 gammas which are going side by side, back to back, and also after some time, because this cadmium, this reaction will actually take a little bit of time because there is a delay in decaying into that, getting a stable cadmium, and then produce this photon. Okay. Now these people did such a simple experiment. Actually, there is a system. I'm not going to bother you with this, but 1950s, you can imagine what kind of instrumentation, what kind of simple electronics that you can. All of you must be knowing what an oscilloscope is, right? You use it nowadays to test signals. Whatever you have an oscilloscope, their system is nothing but just an oscilloscope. Using such kind of a very nice way of connecting up this the 2 principles that I've shown there, they actually first able to identify those 2 gammas which are produced by one system, which is actually shown in this red, and then they also saw, after some delay of 3 microseconds, let us say, saw the neutrino also producing the neutron also producing another. And this coincidence, the delayed coincidence, is what is important, and that clinched the issue. And the instrumentation that they used, as I was saying, is nowhere near LHC, what you saw, billions of millions of detector channels and big instrumentation. Idea to use the instrument that is available, as I said, it is basically an oscilloscope trace, right? Now,
one thing, there
yeah,
are neutrinos you said coming from everywhere.
Yeah.
Right?
Yeah.
Neutrinos coming from the sun, from the Big Bang, from whatever.
Yeah.
How do they know that
this is
these
coming?
are the neutrinos and not some other neutrinos?
Yeah. So what one is asking is that how do you identify? Yeah, how do you identify these particles? How do you identify that they are coming from sun, they are coming from atmosphere, they are coming from supernovae or whatever it is? Okay, you have a few handles. You remember in the beginning when I said one of the parameters I said is energy. The other parameter I mentioned is the direction, right? So if I want to look at solar neutrinos, one sure shot that I have in my hand is they should be coming from sun, right? So if I have a detector in which I have a track of this neutrino produced event, but when I connect there those dots and when I reproduce, if it is in the direction of sun, I know for sure that it is coming from sun. Solar neutrinos are low energy. Let us say the neutrinos which are produced in the Earth atmosphere. Okay. So, for example, energy, there I can make a distinction and say that the lower energy, lower detectors, for example, I use typically like water, which is very light detector, light material for using solar. But whereas for neutrinos which are high energy coming from atmosphere, etc., I use different materials, like what you will see, we use iron and so on. So this is very important to kind of understand what are the metrics that you have in kind of distinguishing. One is direction, another one is energy, and also there are also the interactions that take place. If you said, I said the game is to make these particles interact through using the force carriers, whatever applicable in this case, they're weak force carrier, and then look at what are the products that are produced. This is where theoretical colleagues will already give you certain hints about this is a possible reaction that will happen. Now, in the chemistry too, when you do certain two elements or two compounds you mix, and you will say these are the possible reaction that will happen. Now you will go and do an experiment and see really that is the way or not. So you have to use all the data that comes from a detector. In fact, you have to build your detector based on which type of neutrinos you want to use. If you want to use solar neutrinos, the detector is completely different. If you want to use atmospheric neutrinos, it's completely different design. If you want to use accelerator neutrinos which are produced in the particles accelerators, then you have to build a different type of neutrino detector. Now, what I want to kind of show here is, look at the 1950s. Yeah. Okay. 10 minutes. Okay. 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 Right. So I'll have to kind of speed up, I think, a little bit. But look at even in 1950s, the kind of resolution that they could get on. You remember we talked in the beginning how important to have these numbers. Then only it will clinch the discovery. But it took 25 years later. These guys got Nobel Prize. Unfortunately, by the time Cohen has already passed away, Nobel Prizes are never given posthumous. So only Reines was given the Nobel Prize for this. Okay. So this is the telegram that he sent to the guy. Pauli is the person who actually theoretized the entire reaction here. So they're sent saying they're very excited that we have observed this particular event. Equally great experiment, which by Ray Davis. I mean, just look at the techniques, right? It takes a big, several 100 liters of chlorinated water and then keep waiting on the ground, right? He has a friend by name Bakal who calculated and said, sun will emit because of the thermonuclear reaction about which I talked to you just now. Precisely this many neutrinos are produced per second per, let us say, certain angle. Okay. And he said, okay, fine. I'm going to kind of take water and then chlorine 37. When it looks at this electron neutrino, it's going to produce an argon 37 and an electron. I will wait for this big tank of chlorinated water. Keep counting how many chlorines have become argon atoms. Very painfully counting each atom, right? Because he takes all this liquid once in a few months and then takes it to this some kind of counter, and then he plots on this. Look at 1970 to 1994, almost 25 years. By the way, Ray Davis did in his life only one experiment, and that is this experiment. What did he discover? He said that the number of neutrino his friend told is this, but actually he's observing more about 1/3 of them. Okay, of course, people thought he's mad. How can a chemist? He's a chemist, by the way. He does a neutrino experiment in a particle which will never interact with anything else, right? But he stood his ground. He continued to do this experiment, right? But then later on, there were more, I would say, sophisticated experiments, one in Japan and so on, and which actually clinched the kind of final discovery. And it said that yes, neutrinos are very interesting particles. You remember I showed you those three: electron type, muon type, and tau type. What they do is, as they keep traveling, they kind of transfer or oscillate from one flavor to the other flavor. Okay, so solar neutrinos which are coming from sun, which are of electron type, as they keep traveling to Ray Davis equipment, 1/3 of them have become muons, 1/3 has become tau neutrinos, and only electron neutrinos left was 1/3. And that is what he was able to measure. naturally. So he and the person who actually finally, the experiment which finally made a much sophisticated experiment called SNOW, Sudbury Neutrino Observatory, which has a capability to observe not only just electron neutrinos, but muon neutrinos, tau neutrinos, everything put together. They combined one Nobel Prize for neutrino, for this neutrino oscillation discovery not long ago, 2015. Okay, so this is what the joy of doing experiment. It's not, Arnab was mentioning some time back, more such things should also happen here. This happened in India. This happened by my previous group members in 1965. I was barely 2 or 3 years old. They went down about 2.5 kilometers below a gold mine. They built one detector which looks very simple. You see that there are stacks of there are these, those little circles you see. Those are active detectors. So if there's a particle which goes and hits that, and if I apply certain voltage, it gives a flash of light. They are filled with neon, so therefore they're called neon flash tubes. Okay. Now, if you see this track that is going through and hitting so many of these dots here, right? These are particles, these are neutrinos, which are actually produced in this rock around here. There's a rock wall here. It's a gold mine underground, and that is what it is on left and right side. And you don't expect any charged particle going at that angle, right? If they're coming from atmosphere, they should be at an angle about 70-80 degrees, but this is almost going at horizontal level. And they kind of discovered that this is the type of neutrino which is produced from in the atmosphere, in the Earth atmosphere. That's why they're called atmospheric neutrinos. They are new muse. Okay, this is 1965, and Indians were the pioneers in this particular neutrino astronomy. Neutrino astronomy it is called, because the atmospheric neutrinos were discovered by Indians. Of course, in fact, it was published on August 15th, 1965. Just 2 weeks later, Linus again, their group also discovered atmospheric neutrinos, but we are happy that we were the first. Just 2 weeks, right? I mean, you could take that time to write your paper and send. But there is nothing like who is second. It's always who is first, right? So this is the thing I was telling you. So let us say the cosmic ray particles which are coming from any galactic sources comes and interacts with Earth atmosphere. You can actually see the balloons to give an idea about 30 kilometers, right? And yeah, so then you can see they generate pions. Pions are very they quickly kind of decay into other particles. You can see like pion pluses become muons and new mu's and electrons and gammas, etc. It's like a shower. Like you can see one producing more particles, and you can actually see this is like a typically around 10-15 kilometers above thing. This is like Mount Everest. So when you come down here, you will see shower of neutrinos, shower of muons, shower of all these particles. Now, what we wanted to do was that we wanted to go to a mountain like this, right? This is close to Theni, which is close to about 100 kilometers west of Madurai. In fact, this is between Kerala and Tamil Nadu border. So this is the kind of mountain that we have, and we want to build an experiment inside this mountain to look for neutrinos. How do we do it? So the detector is going to be something like this. What we have is a stack of iron plates stacked one above the other, and then kept some gap between each one of them, into which we are going to insert detectors, which we are going to show today. So it's like a sandwich of a big cuboid with gaps right in between. So there are 56 millimeters of iron plates, each weighing about 4 tons, and there are 4 centimeters of gap into which you insert, like how you do notebooks into a pigeonhole. So it's like a stack. It's iron plate detector, etc. How big it is? It's about 15 or 16 meters high. It's actually a 5-story building tall, and once it is built, it will be world's largest electromagnet, because the entire thing is magnetized using. Can you see these pink coils? These are coils which through which, when you flow current, it magnetizes the entire magnet. I'll show you why we need to do it now. So you see nu mu. The nu mu means the particle which are generated in the Earth atmosphere. When they interact with the either neutrons or protons which are in the part of this iron, it is again going to produce muons and the let us say protons and neutrons. Now these muons, they're charged particles, and as they go through, because of magnetic field, they bend, and you measure the bending radius and you know the magnetic field, you will be able to tell you what is the energy or momentum of this particle. Okay, so okay, maybe I don't know whether there is a time or not. Why I don't see this? How do I come out of this?
You're going to get out of the pointer. Just change to.
Say what?
Just unclick the laser pointer. Yeah.
Yeah. So this is the tunnel that you have to kind of make about 2 kilometers below the mountain, right? You can see that the truck is actually passing through that, carrying these iron plates. And once it reaches end, you have a long, big cavern, about 130 meters long by about 20-30 meters height. So that's where you have a platform which is waiting for you to start stacking of all these iron plates one above the other. And then that is, you literally have to build one layer at a time. And then at some point of time, you of course you also have to start putting the coils, and ultimately the entire detector becomes ready. But what we plan to do is we want to make 3 modules out of this. So 1 module at a time. You finish this 1 module, then prepare the next and so on and so forth. Sorry, I'm not sure I will have enough time. But just remember, this is 4 times bigger than any of the LHC detectors that you have seen. That itself I showed you, that is a very gigantic detector with a human as a scale, but this is 4 times bigger. And you can actually see that module by module how you plan to build it. And after the entire iron structure is done, people will go with these detectors that you are seeing here. They're much bigger, 2 meter by 2 meter in size. They go and keep inserting 1 layer at a time, and then they go up using this setup, right? Just to scare you with the numbers. I mean, it's going to be a gigantic size, but just remember that the amount of detectors that you need, like this here, it is hardly like about half a meter by half a meter. You need to cover about 100,000 meters square of area. It's like about 16 soccer fields. If you have one after the other and you cover the entire detector, in case you wonder how big that is, it's sum total of all the RPCs in the world is only a small fraction of this number. And you need to instrument about 4 million electronic channels. You have to design complete electronics, should be able to read data from this. Okay, the detector is pretty simple. You take 2 pairs of glasses. I think you'll become more clear when you see this picture. And then you flow special gas inside. And then when the particle pass through like this, it produces signal, and which you can see which you can pick up using what you call pickup panels, which again we will show during the demo. And the signals are extremely tiny, and you need electronics to be able to kind of process. And what is important in high energy physics is, since you need 30,000 such detectors, you can't really make them using very costly equipment. You will always use something which are commonly used materials, and materials that you see is like plastic, like some films, like glass, and etc. So that is how we build these big detectors. And okay, I think I should move forward. And of course, you do everything in lab, and you will start with very basic kind of primitive kind of technologies, but then you need to take them into industry to produce them in large way. As I said, these detectors use gas as active medium, so therefore you need to flow a special mixture of gas to all of these. So that is required to be, the systems, entire systems need to be kind of developed in-house. It's not that you can buy from the market such devices. So this is how one detector unit, what you are seeing here, looks like. And you need to kind of, when you have this stack, so exactly how much, another 5 minutes I can take?
5
maximum. Okay. Okay, so 12:35, I'll stop. Okay, so you can see the kind of track that is going through these layers and layers of that. And I need to, as I said, I need to understand the direction in which it is coming, and also I need to understand where is the location that is passing through. The way it happens is, when the layers RPC has resistive plate chamber, it has these pickup panels which are orthogonal to each other, so that it's like a cross wire. So when the particle track goes through, I'll be able to get X and Y direction in each of these layers. And if I put those points on a graph sheet, I'll be able to get in the direction in which it is, I mean, the track it is going. But whether it is up or down, I use it to do like a time stamping. So as the track comes down, when it is reaching various levels, I'll put a timestamp on the track. It looks very simple to you, but I'll tell you how difficult it is. These particles pass through at a speed of light, which is 3 into 10 power 18, 3 into 10 power 8 meters per second. So those 10 centimeter, it will cross in few hundred picoseconds. So the stopwatch that I have in my hand should be able to timestamp at that level. So these are electronics that are required to be built, and everything, of course, starts with, you can't go to Lamington Road and buy all these electronics, obviously, right? So what you do is you sit down and start designing what you need, right? These electronics is something which you have to design by yourself. And for us, we have really bright students, graduate students, PhD students who come and say, okay, what are the kind of things that we require to have? Yes, this is the timing, this is the resolution, this is the kind of signal that we have. They make such a block diagram and they design the entire chip. And unfortunately, we don't have big industry in India who can make these chips for us. We send to Europe and say, please make a chip for us. Okay, it's like an integrated circuit made specially for us for a specific application. It's called application specific integrated IC, integrated circuit, right? So those are the ICs that you can see, which are actually made by us, and you make into a board. I told you how difficult it is to timestamp those pulses as signals as they're going. Here, another student from IIT Madras, she works with and says that, okay, I can actually give you a device which can timestamp at 125 picoseconds. I need 200 picoseconds, but this device works better than that. And that is exactly how you timestamp. Now, if some signal is coming from top to bottom, the time will keep on increasing as you go from top to bottom. If the neutrino coming all the way from the other side of the earth, which can happen, and going upward direction, then of course the time will tell you whether it is up or down. These two pieces of information is very, very important. We all, again, we build many application specific integrated ICs. We also use what is called field programmable gate arrays. These are like circuits, like a white canvas. There is nothing inside that, like unlike some of those gates and counters, etc., which you buy in Lamington Road. You actually take it to your office, and then I can design, I can program it the way it should happen. It should work as a digital device. Tomorrow I don't like the design, I can erase it. I can actually make a new logic into it, and I can put it in. These are modern digital programmable devices, right? So we use a lot of them in our experiment. We actually designed and manufactured many such application specific integrated circuits. As I said, these are not something which you can buy from market, but once you design, they can be used for many other applications beyond science. So lots of such electronics is designed in the group. And now when you put everything together, and when you allow a cosmic muon passing through, it kind of leaves a track like this. Of course, this is artificially juxtaposed on an event, but I can even show you probably a real event. Even such a modest small detector which we built to check everything is working fine, you can see beautiful tracks that we are able to kind of track them and record them. That tells you that our detectors are working fine. Even in such a small detector, you can see very interesting events. There are 3 muons parallelly going through in one such a small detector. So this is quite interesting thing. You can use RPC to kind of do like a tomography. The detector that is sitting horizontal, millions and millions of cosmic rays are passing through, literally doing a tomography like an X-ray for a human. And you can see those white spots are the place where you have those little buttons to keep them in parallel to each other. Okay, how do you know that it will work for that big gigantic detector? You build like a baby detector, a small one, exactly the same technology, same RPC detector, same electronic, same magnet, and so on and so forth, and see how does it work. And you will be feel very happy, because when you magnetize this, when you produce 1.3 Tesla magnet, and you can actually see the tracks which are like going straight because there is no magnetic field there, they're nicely bent, and we feel very happy about. We know that things really work when we kind of do it in the in the real experiment. So I think I have to skip. These are all for the spin-offs that I have, but I'm sorry I had to skip. I just want to just one last slide. You will wonder, neutrinos are something which, like, as I said, it could be a mad kind of a pursuit for many of you might be thinking, but there are always many such spin-offs which will happen. What I skipped are the detector and electronic spin-offs that will happen, but as such, neutrino themselves, nowadays, for example, we use electromagnetic radiation for our cell phone and communication, but it has certain limitations. For example, if somebody is there below, let us say in water and maybe in submarine, etc., it is very difficult to communicate. Now, neutrinos being particles which are not stopped by any amount of matter, can we really use neutrinos for communication? It looks like a scientific fiction today, but there are guys who actually made such an attempt in one of the experiments at Fermilab, and they were able to kind of pass certain small message called neutrino at astonishing speeds, of course, 0.1 bits per second. So actually, one bit took 10 seconds to pass. Okay, in the scale of gigabits. But I'm sure as a rule of, as a proof of principle, this was done. You could also kind of monitor the spent fuel, which is a major concern for regulatory agencies in, which is the plutonium, which is produced by various countries. And these detectors, which are like a network, like a GPS constellation of detectors, could also be used to kind of produce, monitor whether there is somebody who is producing these things illegally. And last but not least, that probably a network of neutrino detectors could also be used to understand what are the reserves of radioactive materials that you have on the Earth. So I'm sorry with that I had to come to. I just want to say that instrumentation is such a unpardoning in some sense that you really need to kind of check and design, check, verify really well. Then only the experiments will be successful. You are looking at Higgs boson, but if there is a wire which is loose, probably it will discover something else. It happened some time back. Somebody did an experiment and said that actually neutrinos travel faster than light. It was published all around. There was a national world over. Actually, there was a seminar. It was great discovery because you never know that you never heard that something can travel faster than light in vacuum. But later on, they found out that the problem is with an optical connector, which had made a contact problem, and they had to withdraw back that discovery. And similarly, I mean, this is an example of Chandrayaan. You can see that the things traveled by 384,000 kilometers, and short of 2 kilometers, unfortunately, the mission has to fail because obviously there's something which we didn't understand. I'm not showing this as a failure, but I'm saying that it's a learning, but that is how it's important to have kind of things. So people, if you later on you want to understand opportunities for INO, they're here, and how to contact INO, some of these contact details, etc. They're all given here. So thank you very much. Yeah.
Okay, thanks a lot.
Yeah.
Satya.
Yeah.
Actually, just put some other sliders here.
Yeah. Yeah.
Keep it there. Keep the.
Yeah. Yeah.
No, contact.
I think this is better. I think this is better.
Okay, so we get questions from all of you. Just remember that we have there's a play after this, so we will have to leave. We might have to take these out to show people.
Okay.
I'll quickly finish off with the questions online. Do neutrinos always travel in straight lines if they don't interact with things? Neutrinos travel in straight lines, yes. And why do you have multiple RPCs and not one large RPC?
I mean, well, I don't know if the question is multiple RPCs in one platform, one layer, or I guess that is the question. It just no, it's just a practicality. I mean, you have a detector which is 50 meter by 16 meters by 16 meters. Okay, so you have 50 meter by 16 meter is one area. It is very tough to kind of make one RPC. So you need to make small units. In fact, 2 meter by 2 meter itself is it's like a papad. I mean, this is 30 centimeters by 40 centimeters. Now imagine there are 2 meter by 2 meter. If you come to my lab, I'll show you. You hold in one hand, it just breaks because they're made of glass, and it's a very difficult to kind of handle it. So that's why we make multiple of them. Of course, the bad thing is that if you make many of them, there will be some gaps in between, which is dead space, but we can't avoid that.
Okay. And do these three flavors of neutrinos have different masses?
Yeah. See, each one of these flavor is actually made of a mixture of what you call mass eigenstates. So let us say take nu e. It's made of nu e or nu mu or nu tau. Each one of them is made of a mixture of nu1, nu2, nu3. Let us say these are mass eigenstates. So it's a mixture of them. And as they travel, it happens that this nu1, nu2, nu3, that composition keeps changing because of the matter effect. And that is how it gets into another flavor.
So,
yeah.
Let's see if there are questions from the live audience. Basically, what we could do, Satya, is if you wanted to very quickly show them.
Yeah.
We just because we have to pause the live stream for
Yeah.
Right.
Okay.
What we will do is I'm just going to hold this down here.
Okay.
And you can basically probably say what these things are.
Oh, okay.
So
Okay.
I'm just gonna, yeah.
Okay, so what you see here is what I called as a resistive plate chamber, the main detector for the INO ICAL experiment. It's made of two glasses which are kind of held side by side. Precisely.
Can you stop screen share? Then this will be full screen. Just stop the screen share.
Yeah. So the glasses are held parallel to each other with the 2 millimeter precise gap in between them, and you can see that all sides you kind of seal them, and this black stuff that you are seeing is a kind of it's a graphite coat. On that I apply 10 kilovolts field. So 10 kilovolts is a very big field. I mean 10 kilovolts across 2 millimeters is 50 kilovolts per centimeter. So we flow gas through this special mixture of gas. So I showed you, for example, one of the neutrino decides to interact with iron and produce, let us say, a muon. The muon, when it's passing through, it ionizes the gas inside and produce signals on these panels. These are panels. How do you place panels? You place one panel like this, right? You see the this strips are on this side, and I place one more panel orthogonal to this, perpendicular to this, one on either side. Okay, and then when a muon pass through, the signal that is produced will be produced in one coordinate here and produce another coordinate here. So it will give me an XY thing. This is a beautiful detector because if you want to do similar things in other detectors, you need to make two layers of this detector, one on X side and one on Y side. Here for the same detector, you get XY coordinates, right? So this is just a bare, what to say, earlier design of the RPC. In fact, you can say this is the first RPC I made in this country. So it's way back in like 2001 or somewhere. Okay. But this is what I want to kind of tell you. The signals that are produced at these points of time on these wires are extremely tiny. So I said you require to kind of amplify those signals. I'm not sure you can actually see these little amplifiers here, which is about 2 millimeter by 2 millimeter, and the entire board itself is only an inch wide because we want to minimize the space, dead space that you are taking for electronics. You would like to make an active area as much as possible. The question that was asked, I wish I could make an RPC which is 50 meters by 16 meters. So electronics has to be good, low power, very high speed, but most importantly, it should take very little space. So it's very important. That's why you need to design your chips yourself. You can't use ready-made chips. So actually, let me show you right here. So this is some time back, let us say 2004 or 2005, that we designed an 8-channel amplifier. 8-channel. You will see 16 chips here because 2 chips will do 1. Okay. Now you can hold. It's quite heavy. It draws a lot of power, and this is the kind of area. Now this one is the same thing it is doing, 8-channel amplifier and discriminator. I mean, there is a logic conversion. It does many more things, but this is the kind of chip. So that is the development that we need to do. I want to show you this funny looking board here. This board is like a triangle shape. The simple reason why, because we want to minimize the detector is squarish, right? Or 2 meter by 2 meter. I want to cut a very little part of this and put this guy here. Otherwise, what happens if I make a rectangular one? I'll be occupying a lot of dead space, right? I don't want to do that. So you kind of put it here. But look at this little board. This board has a kind of thing on the perpendicular. It actually picks up 128 RPC signals on this. Each of this track is only 0.6 millimeters. Now you have big 2 chips. One chip will give you precise the timing that I talked to you about. The other one is so-called field programmable gate array, which you can do data acquisition, etc. The data is completely acquired for 128 channels and then sent through this connector. Probably you are aware, you would have seen, this is your RJ45 connector, Ethernet connector that you see on your computer. So the data number crunching and all done, and the data comes through this. And this is like your computer, it has an IP address. There are 30,000 detectors, there are 30,000 IP addresses. I can sit anywhere in the world and I will be able to control each device in Madurai, in particular underground detector, and what it should do. So this is a very cool thing, right? Okay. We don't even spare, by the way, so even a power supply that is required, which is actually mounted write on this like this. Okay, I took it out because I wanted to show this. Even this we design our own. We don't spare even a power supply that is required to power the RPC. We make our own kind of thing. Again, you can see this square shape, the triangle shape. That is because on one side I want to put this one, and on the other side I want to put the power supply here, and everything should be integrated, and it should be able to work with minimal disturbance to the space. Okay, so that is a kind of thing.
Okay.
Yeah.
So I think with this, we will. Thank you, Satya. We will end our live stream. So guys in TIFR, you can end the live stream on YouTube and Facebook. Thank you. Join us again in 2 weeks. We'll follow up with what is there. And I think we will break for chai, and you can also take a look at this. Thank you, Satya. Thank you again.
Thank you. Yeah, thank you, Chayan Bhai, and also thank you all of you. I hope we'll also have a little more interaction after this. Yeah.